those things actually.
Okay, so couple things. Be a short video for you guys today. We were talking about why some of these equations don't really impact your shaded region, and that if that happens, it's not a big deal. There are a lot of factors if you are running a business that don't impact your decisions, even though you might think that they do. This is a situation. This was number 4 on the homework, as well as that first one on the homework. If that happens, yeah, I would probably be a little hesitant too. I'd probably be a little nervous because I'm assuming they should intersect, but just check your math. If it happens, it's totally possible that happens. So when these both shaded down, there was no intersection. That's okay. Occasionally, that does happen. Second question on the table was about Gaussian elimination. So let me just grab a problem. Tell you what, I'll just make one up. So it'll save the problems for you. And so what if, and again, Gaussian elimination is kind of the where you got the elimination method from. But the elimination method was just really quick, and we were just trying to get answers. All right, we were just trying to eliminate an X to get an answer. A Gaussian elimination model is a little bit more formal. So remember, when you're doing, and I will give you one, when you're doing a Gaussian elimination problem, to me, it's about your form. So I'm going to give you some 3-variable system, and I'm going to want a 0 in the beginning of the second equation, and then 2 zeros at the beginning of the third equation. And I want to see that, okay? Because the next chapter we do is going to be on matrices. And on matrices, we're going to be using that Gaussian elimination to turn your matrix from it's going to represent a system, but it's going to be a really ugly matrix, and we're going to put it in what we call row echelon form. And row echelon form is basically that whole Gaussian elimination model. So you're going to have to be able to do that and create a new matrix. So again, don't get sloppy. It's not just about getting an answer. There's lots of ways we can solve and get answers. You're showing me a model. So the form that you use is going to be important. So I'm just going to make one up and walk you through this again. So what if you had and my guess is this math is going to be a little ugly because I really didn't think about this problem, but I'm going to try to give you nice, neat, whole number answers. So we'll check it. Okay, I think I'm good. Our answer should be that point. Okay, so Gaussian elimination wants this to be a 0, this to be a 0, and this to be a 0. So we're going to go through, it's basically a 2-step process to eliminate, using basically elimination, these 3 values. Now, as I eliminate these, you're going to see that all of these 3 and those 2, all these other values are going to change, right? But when you're done, the hope is you're going to have nothing there, and you're going to have z equals something, or maybe 2z equals something, and you'll be able to solve for z easily. And then you'll take that z and you'll plug it back into this equation. Well, this number will be gone. So if I know z and I plug it in there, I should be able to find y easily. And then if I know y and z, I can take the y and z and plug them both in here, and I should be able to find x easily. So your goal is to use what you know about elimination to make that, and that go away. So what could I do to this problem to make that go away? And remember, I'm going to be using these 2. I guess I could change it with this one too, but I'm going to always probably work with these 2. And by the way, before you get started, these are just 3 equations, right? If you're like, oh man, it'd be a whole lot easier if this one was on the top. Well, if you want to do that, put that one on the top. I don't care, but do all that arranging at the beginning. I would probably avoid that stuff in the middle. And again, I'm looking for form. So I personally, I know the elimination method, and I know my rules of algebra. I can multiply any equation by any number anytime I want. So I'm going to multiply this top one by a -2, and I'm going to write that result right above it. So because I want to cancel -4 with 4. So that times a -2 would give me -4x, +2y, -6z, and -18. And be really careful with the math, because if you make an error on this, it's just going to get really nasty. And I will give you nice, neat, whole number answers so that you know if you're right. Okay, so you're going to get answers like 1, -2, 4, 2, 5, -3. You're going to get decent looking answers so if your answers are like 27 12ths, 15 97ths, you've screwed up. But even if you have, show me your work, because I might look through there and go, 2 times 2 is not 7, it's 4, silly guy. If it's a careless error that I can see, you'll probably just get dotted, right? If it's more than just a careless error, if it's multiple ones, you might get slashed through. But show me your work, and you'll be okay. So now I'm going to add this row to this row, the red one to this one, and what do I get? 0, and there's the 0 I wanted. 3y, -7z, and -15. Okay? So I have basically used the elimination method to add these together. Well, now I want to make this a 0. I want a 0 there, a 0 there, and a 0 there in my new system. So I'm going to want one here, here, and here. So my first step, my first process, I'm going to get zeros here. And then my second process, I'll add the 0 there. So I'm going to say, well, in this case, I would rather this be a -2 to combine it with that +2. So I don't need that red equation anymore, right? So I'm going to multiply this by -2, -2x, +6y, -4z, -2, because that's algebra, I'm always allowed to do that. And I'm going to combine this purple one with that red one, which gives me 0. That's what I wanted. That and that's 5y. That and that's -z. And that is 7. And then I've got the 2 zeros I want. I don't need this red thing anymore. Although you're welcome to leave it there. I'm just cleaning it all up. And then I'm just going to carry this first row over. So 2x minus y plus 3z equals 9. And the first step of my Gaussian elimination is finished, right? 0, 0. Now I want that to be a 0. Now don't look at the first one and the last one and go, oh, well, if I multiply that by a 5, that would give me a -5y and a +5y, and that would add and give me a 0. Because if I do that, what's it going to do? It's going to give me also 10x and 0 is 10x, and I'm going to lose that 0. So on the second step, always use these two, okay? And also I see people all the time that go, man, it'd be so much easier just to multiply the bottom row by a -7, then these will cancel. You're right, it would be, but I'm trying to show the model of Gaussian elimination, which is 0, 0, 0. I'm trying to do form here. So stick to your form, right? Because there's going to be, in next chapter, there's going to be a process called reduced row echelon form, or even row echelon form, that it's going to basically mirror this. So if you can get this stuff down now, next chapter it'll be child's play. Okay? All right, so I gotta, in this case, to make that a 0, I'm gonna have to multiply that by a 5. And that by a -3. Right? Add those two blues together. And I'm just going to bring it down here. This is the top row. And when I add these, and I'm going to leave a little space right here for row 2. I'll fill that in a second. When I add those two together, there is I already have zeros here and here. When I add that to that, I get another 0 in the third row. I get a -32z. And I get a -96. and then I'm going to bring the second row down. And I can bring the second row it's blue down, but I could also take this blue one, divide it back by 5 and get to the red one. And I like the red one better because it's less numbers, smaller numbers. The math will be easier at this point. So I bring the 0, 3y, negative 7z, and negative 15. So at this point I have the 3 zeros. Well look, this system has the same solutions because you've done elimination as the original one. But now it should be easy to solve. So I start with this and go, that would give me, when I divide by negative 32, z is 3. And it is 3, right? We knew that. Although you won't know that, right? And then once I know z, I can take that value, plug it back into the second equation. They call that process back substitution. Really thought long and hard about that name because you're substituting it back in. And that gives you 3y minus 7 times your z value. And I can take that negative 21, add it to the other side, which gives me 6. So y is 2. Great, I've got the y value. I knew was going to happen, although you won't know that. And then the last step, I'm going to take the z and the y and plug it back in. And that gives me 2x minus that y value plus 3 times the z value equals 9. And I'm going to take this and I get 2x, and I'm going to subtract that 9, add that 2, and I get x equals 1, which again is confirmed. So my final result is the point 1, 2, 3. And that's Gaussian elimination. And again, remember, I know you know how to solve this. You could use Kramer's rule to solve this. You could do substitution to solve this. There's lots of different things you could do to solve this. That's not my goal on this problem. My goal is for you to solve it this way. Are y'all with me? There are classes in college, like coding theory, where literally you just manipulate matrices and use, although in coding theory you're using zeros and ones because it's kind of like program-based, like computer-based, but you're using these processes, this Gaussian elimination process. Like I remember doing all of this in a class. Like my son's about to have to take a random math elective. I'm like, dude, take coding theory. The whole class I've already taught you, because you learned it in this class. And they spend 3 days on this in college, which is kind of funny. But the people who might take this aren't as, I don't think it's as a collectively smart group as this. So it's just random folks, right? Not all math teamers. Good. Now, the part that's tricky about this, the part that's harder, and we talked about this in that video, is what happens when you're solving this. And this is a big what if. But what happens when you're solving this and instead of getting 3 zeros, another variable cancels? So that's the big part that becomes trickier on this test. So what would happen if, as you're solving, you add these 2 blue equations? Again, this is a big what if, and you got a 0, obviously 0 and 0 is 0, but then that gave you a 0, and then this also gave you a 0. What does that mean about this problem? There's no solution, because 0 doesn't equal negative 96. So if that were to ever happen, again, I'm going to be a little nervous about that because it might be just a math error, right? So if that were to happen to me on this test, or happen to you, if that happens, go, wait a minute, that means it's D&E. But I would probably go back and double check my math, right? Really be careful and say, okay, when I multiplied by 5, was it really negative 35? Was it really negative 75? Double check your math for a second. Make sure that that really happened. But if it's not true, not equal, you'd say D&E. Now, that part's not that hard. This is the part that's a little hard, or a little bit trickier. What happens when everything cancels? When everything cancels out, this is the part that if somebody's going to miss on this test, this is probably it. What does that mean? Not no solution, but infinitely many solutions. But you can't get away with just saying infinitely many solutions. It'd be like saying, hey, what's your favorite food, Ella? Oh, there's so many. No, what's your favorite food? There's so many. You haven't answered the question. I mean, maybe I've gotten some insight into, hey, I really like everything. Like my mom, it's kind of weird like this, but she would eat anything. As a kid, I remember going, orange peel. And she would eat an orange peel. And I'm like, okay, that's not bad. Banana peel. Now, she wouldn't eat the whole banana peel, but like she literally would, it didn't matter to her. She could eat anything. And as a kid, I was like, dude, I was very picky. Like I didn't like a lot of even the stuff I like today, I didn't like back then. But you haven't answered the question. I want to know, it's not all reals, right? Remember, what do these equations stand for? Not lines. These are planes. So if I have 3 planes, how can 3 planes intersect in infinitely many solutions? They would intersect on a what? On a line. Like, look at this plane right here, this wall. And then the floor is a plane. They intersect at the seam right there, right? So if they intersect right there, that's an infinite number of solutions, but that is a line. Problem is, you don't know how to give me an equation of a 3-dimensional line. In the video, I talked about parametric equations. That's what they are. Well, the way we go about doing that is kind of a manipulation of what we know. We're going to write it as a point, but the point is going to have variables in it. So what we do is kind of what we did before. We start with this. We go, well, I do know this. X is X, Y is Y, and Z is Z. That's a certainty, right? It's like I am me, you are you. That's obviously true. But I'm going to start with one variable. So I'm going to go, well, if I've done it this way, the first variable I would have solved for was Z, isn't it? So I'm going to start with that. I'm going to say, all right, Z is Z. Now, what if I had said Z was 2? What would you do next with the 2? In this process? Plug it back in. We'll plug the Z in and solve for Y. Now, when I plug the Z in, does it do anything? No. But you can still solve for Y, can't you? So let's do it. We solve for Y. Sorry, 7Z. By adding the 7Z and dividing by 3. Yeah, this is going to be terrible. Sorry. So that gives me Y equals -5 plus 7/3 Z. So I've got the Z now in terms of Z, and I've got the Y in terms of Z. Now, what would you have done on Gaussian elimination if you knew the Z and the Y? What would you have done? Plug them back in and solve for X. Well, that's what you're going to do. You're going to take this Z and plug it in there. I don't have room where I put it down there. So you get 2X minus my Y equation, which is a Y value, which is that, plus 3 times my Z equation, which is Z equals 9. And you're going to solve that for X. So it's really the same thing, except you just don't have a number to plug in. You're plugging Z in, solving for Y. Then you're plugging that expression in, solving for X. But all of your answers are going to end up having Z's in them, most likely, unless by some random chance the Z's cancel. So for here, you end up with 2X plus 5 minus 7/3 Z plus 3Z equals 9. So I'm going to subtract that 5. I'm going to find a common denominator here, make that a 9/3. That's a positive 2/3 Z. I'm going to subtract that. That gets me to this. And then I'm just going to multiply both sides by 1/2. And that gives me X equals 2 minus 1/3 Z. So and again, I probably would try to make these a little bit nicer to you than these fractions, although these fractions aren't that bad. But I just made this up off the top of my head, right? We were just making junk up here. And again, this problem's not going to do this. This is a big what if, right? So if this did happen to you, your final answer would be, all right, my X, 2 minus 1/3 Z. My Y, -5 plus 7/3 Z. My Z is Z. And that would be all of the points. And what does Z mean? What could Z be? Anything you want it to be. So if I plug any number in the world in there for Z, you get a point on this line. So really a better way to say it would be, this is the solution where z is all real numbers. But I'll just take the generic point. And that represents the system of linear equations. That represents the parametric equations of this line. And when you learn parametric equations, it's not much different. You would just say the parametric equations are 2 minus 1/3, but you would probably use a different variable like t. Y would be -5 plus 7/3 t, and then z would be t. You'd probably just replace those with t's and write them as x, y, z. Those are parametric equations. And we'll do a little bit with parametric equations when we do projectile motion, but we're going to be looking at just two-dimensional parametrics. And we're going to kind of look at it from a physics perspective as well. Anybody else on anything we've done want to have a quick chat about? Nobody? How about that Urban Meyer hire? Huh? Nobody?
It's not there yet.
Not there yet. It's looking that way though. How about that Auburn Tigers win? Any Auburn Tigers out there?
First SEC win.
Yeah. Granted, we were beating also no SEC win team, but how about Sharif? 27-13. Averaging a double-double in SEC play. Yep, the future's here. All right.
Can you do a partial fraction decomposition?
Partial fraction decomposition. Absolutely. Ella, carrying the day today.
So, yeah, Haley contributes to that too.
Haley, okay, nice. Okay, so partial fraction decomposition. Remember there are a couple of rules, right? I'll throw a couple of them out there and then we'll solve one completely. You'll be asked to solve one completely, or not solve one, but to rewrite one completely and actually find the A, B, C, whatever. But you'll also be asked just to expand them without solving, all right? Just because I want to make sure you understand the processes. So the first rule you got to make sure about, what do you do if the power in the numerator is the same or bigger than the power in the denominator? You got to do long division. So go ahead and do your long division, and then you'll end up with some whole number looking things and a fraction at the end. And then at that point, work on the fraction. But if the fraction's power on the bottom is bigger, then you can jump straight to the partial fraction decomposition. And who really is going to need to know how to do this other than this test? Future B, C, Cal students will need this, or possibly future Calculus 2 people in college. All right, so what if I gave you something like this? And you had a the first thing you have to do is make sure everything is factored completely. Is there anything more you can do to this to get it factored? I don't see anything. Looks pretty factored to me. I mean, you might look at this and go, wait a minute, that might, but wait a minute, that's x to the fourth and x to the first. I'm not going to make you do like synthetic division to check possible rational roots to see if it factors. We're not doing that in this chapter. All right, so right here, what are the rules for breaking this up? How do you view x cubed? Do you view it as a cubic? A cubed factor? Is that a cubic or is that a linear cubed? So we're going to look at that as if it was a linear cubed, just like I look at this as a linear squared. So if I break that up, how do I write x cubed when I break it up? X squared, x cubed. And since it's linear, that's being cubed, what do I put in the numerator? Constants, 1 power less. 1 power less than a linear is a constant, so A, B, C. All right, takes care of that. This is a linear squared, So again, linear, linear, 3x plus 1, 3x plus 1 squared. And since they're linear, what goes in the numerator? Constant, constant, d, e. But this is a what? A quartic. And since it's a quartic to the first, then I need a quartic factor, but what would be in the numerator? Cubic. So I'm going to write 5x to the fourth here, minus 3x plus 2, but what would have to go here? Fx cubed plus gx squared plus hx plus I. Are y'all seeing that? Yes, no? So if it's cubic, you need a quadratic, ax squared plus bx plus c. If it's quartic, you need a cubic. Whatever, I doubt it'll go any higher than that. If it's squared, you need a linear. Now, I'm not going to ask you to actually go and find all 9 of these variables. No. I would give you something much more tolerable to do. Does everybody understand this part? Okay, so here might be one that I actually ask you to do completely. So what if you had there's no telling how bad this is going to end up. Trying to be aggressive. All right, do the partial fraction decomposition completely for this. Now, what would you have to do first? This is going to be horrible. We're going to go with it. You're going to have to do long division. All right? Now, again, I'm not suggesting that I'm going to give you one like this, but if I had to do long division, that means I'm going to have to figure out what the heck that is, aren't I? All right, so let's just say we knew that this was x cubed. I tell you what, I'm just going to do it. X cubed minus 6x squared plus 12x minus 8. Let me make sure about that. I'm going with it. All right, and I'm dividing that into this. So x to the fourth minus 3x cubed. I'm missing an x squared, so 0x squared plus 2x minus 4. So I would have to do this first. Are y'all with me on this? So here we go. You'll see that it's not that bad. It looks bad, it's not that bad. So what times that gives me this? A single x. X times everything. Be careful about this. We don't want to mess this part up. And then the whole rest of the problem is just junk. What do we do once we write that? Change your signs. And that gives me 3x cubed minus 12x squared plus 10x. Drop down to negative 4. And then what times that gives me this? 3 times that. And then once again, change your signs. And this 6x squared minus 26x plus 20. I'm going to place that over my divisor, which is x minus 2 cubed. And I have done half the process. Now I've got to do what? Break down this. But when you're done, don't forget the x plus the 3. Okay? So how do I do now this partial fraction decomposition? I'm basically going to go, all right, I know that this is x plus 3 plus that, but I am now going to break down this part. So let me just, everybody got that who needs it? It's on video, I guess you can go back and look. how do I break down this fraction? So I've got a linear cubed. So linear, linear squared, linear cubed. And if it's linear, I have what on top? A, B, C. So what would you do at this point? I'm going to multiply through by the common denominator, which is whatever that is. All right? Whatever that is, multiply through by it. And what does that leave me? That. When I multiply the right side by x minus 2 cubed, I'm left A, but only one of the x minus 2's cancel, leaving me 2. Here, 2 of the x minus 2's cancel, leaving me one of them. And here, all of them cancel, leaving me C. So, how can I solve this? There's lots of ways we talked about in class or in the video, whatever. Somebody help me with something that would be nice and neat and could help me out. Plugging a 2. I love that idea because plugging a 2 in will eliminate any A or B or C or whatever that has an x minus 2 in it, which is all of them but C. So great first start. If I let x equal 2, then this gives me 6 times 4, which is 24, minus 26 times 2, which is 52, plus a 20. That goes away, and all I'm left with is C. So C equals what, negative 8? And I've got my C value. And the second I have my C value, I can change that to a negative 8 and I'm on my way. Now what could I do? I showed you a little trick that might be helpful. Say it again?
There's only one x squared here. So your A would have to use it.
Great idea. Y'all seeing what she just said? She said, if I did multiply all this out, what would be an x squared term? Is this going to give me an x squared term? No. Would that give me an x squared term? Yeah, but it would be x squared minus 4x plus 4 times a. So the only x squared term I would have if I multiplied all this out would be ax squared. Right? And if I look at the left side, the only x squared I have is the 6x squared. Well, if the right side and the left side are going to be equal for every value of x, what does that suggest? A is 6. Great. Are y'all seeing that? Now, if there were multiple x squared terms, well, then you're going to have to be careful, right? I mean, if you look over here like, well, that's got an x something cubed. So yeah, if you multiply it out, there'd be an x squared in there. And if this was x something squared, yeah, there's going to be an x squared in there. Then this wouldn't be that easy. But if you see a gift like that, take it. Because now I have A. And I can plug it in. And at this point, I'm home free because I only have one variable left, don't I? So how would I find B at this point? Plug in any freaking thing you want at this point. Because no matter what you plug in, now I'm not going to plug 2 in, because then that gives me negative 8 equals whatever, and it's not going to help me. But plug in any other number you want, and all the x's go away, and you're left with B. So at this point, what's the easiest thing to plug in? I'm a big fan of 0, right? Because it makes all the x terms go away. So now I'm going to say, and I can do it down here, if I let x equal 0, I get 20 on the left. I get, now be careful, I get negative 2 squared, which is 4 times 6 is 24. I get negative 2 times b, which is minus 2b, minus 8, and I can solve for b. So I end up getting what? 2b equals negative 4, b is negative 2. Yes. So now that I have my a, my b, and my c, right? I can go back here and say, all right, the A ended up being 6. The B ended up being negative 2. The C ended up being negative 8. But that's not my partial fraction decomposition. It's that and what? Plus the x plus 3. Now, sometimes you didn't have to do long division, so you wouldn't have to worry about that. But that would end up being my partial fraction decomposition. And by the way, I would encourage you not to go back and start changing your math, because then I can't see your work like I did. I just ran out of room down here. But on yours, I would have left this like it looked, and then on the bottom, I would have just written my answer, or maybe out to the side. I'm just running out of room and trying to get it in there. Does that make sense? But if you don't have a situation where you have to do long division, which you may not, we'll see. But if you don't, then don't bother with the long division, jump straight to this. And here's the downside. If you don't recognize the long division, you'll actually find the A, B, and C correctly. You just won't have this part. But you will get taken off for not knowing that. That's important. Are y'all good on this? Need to see any more? Sometimes they're much easier than this, because when you factor them, you don't have the same factor so many times. Right? You'll have something like x minus 2 here and an x plus 1 there. Well, those are easy because you can go, all right, if that's, I can let x equal 2, I can let x equal negative 1, and you can find your variables pretty easily. This, to me, would be a trickier one. Anybody else? On anything? Y'all feeling good about it? Yeah? Isn't the light great in here? Just pouring in the morning. If it's blinding you, we can pull the shade. If it ever does, just pull, yeah, just. Like at 1:30 or 2, it's blinding. I can't even see my screen. If the sun's out, I just pull that screen back a bit. All right. Yep.
It says use a graphing calculator to solve. That won't be on there, I guess.
Which one?
3.
Yeah, that will not be on there, but I actually do want to talk about that. It's not a graphing calculator question, but I do want to make sure this is a huge calculus concept. Okay? So, it says use a graphing calculator to determine the number of solutions. I'm going to write this 2 ways. It says base 10, but I don't need to say that. Now I have a question. Does anybody have a problem with what I'm about to say? If I were to ask you to solve this, doesn't a system of equations work? I mean, it's a system, right? And if y equals that and y equals that, then I should be able to say sine of x equals log of x, correct? And isn't that what I have right here? So if I give you this, couldn't you also graph both these curves on your graphing calculator, right? Graph this, and anywhere it crosses would have been a solution. That makes sense, right? Well, if I give you this, then go backwards. If I give you something like this and they're equal, then couldn't you argue that if this can become this, then why can't this become this? Right? I mean, think about it. If these are equal, if they're equal to each other, couldn't I just say that, hey, if they're equal, then that's the same. This could be a y, this could be a y. They're both y, if I name them both y. And then I could graph that and treat them like separate equations and count the solutions. Does that make any sense? In AP Cal, you will get situations all the time on a graphing calculator portion. You might be doing the mean value theorem, or you might be just doing some random thing, and you'll get to the end and you'll go, I can't do this mathematically. Like, you do not know the math, nor do I. Maybe I do with calculus. But you do not know the math to be able to solve this without a graphing calculator. You don't. But my calculator does. So if you ever get to the point where you're like, I can't factor this, I can't use a quadratic formula, synthetic division didn't work, nothing worked, and hopefully you won't even get that part. Hopefully you'll look at it and go, that's ugly, I'm holding a calculator. If you're holding a calculator on any equation you can't solve, graph that, look for the intersections and solve them, and you'll get your answers. This one made it even easier. It didn't say solve, it said how many solutions. That you actually could do. Because look, I could graph this manually, sine curve. You might remember doing this. Isn't that a sine curve? And this is how, what, one period? What's one period on a basic sine curve? 2 pi, so about 6-ish, 6. So another pi would be about 9-ish. So maybe this is about 10. So maybe 6-ish, 9-ish, about 10. And the reason why I'm only going up to 10 here is this is log base 10 of x. And by the way, this only goes to a height of 1, right? And a depth of 1. How do I graph log base 10 of x? What points can you graph on a logarithm that are easy for you? 1's great. What's log of 1? So if this was y equals, when x is 1, y is 0, well, if that's 6 and that's 3, this is about 1, so there's a point. What would be another point? 10. If x is 10, y is 1. If x is 10, y is 1. There's another point. And what do logs always have? Vertical asymptotes. So this graph looks something like this, right? It hits that, heads over, and at that point it's higher than the amplitude goes. So how many solutions did it have? 3. But could I have solved that on my calculator if I really had to know those points? Guys, if you ever, or even better, you know what you could do? I do this actually. Rather than graph them as 2 equations, I do this. I just take this and subtract the sine x, although I can't do this graphically. If I subtract it, then all I have to do is say, I'm just going to graph one equation and find the what? If it's just one equation, you're not finding intersections, but what are you finding? Zeros, where y is 0. Because you're basically replacing the 0 with a y, and you're just graphing that one equation. I don't have any idea what that one equation looks like. Some weird combination of these two, right? But you just look at where it crosses. But it'll cross in 3 spots. So you'll see it go boop, 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 cross in 3 spots, whatever, and you'll go, oh, just 3 solutions. So I normally do this. I just move it over, graph one of them, find the zeros, but what you can also do is graph each one. But you don't have a graphing calculator test. But you should be able to solve that. That's something you should be able to do because you know how to graph a sine curve and you know how to graph a logarithm. I think. All right. We got a video after all.